Howdy everyone, welcome to Chapter 7, the Periodic Properties of the Elements chapter. This chapter, thankfully for a lot of people, light on the math. When numbers are involved, it's more qualitative. Is it number going up or is the number going down? But there aren't very many equations. There's no real formulas to figure out things. So for a lot of people, Chapter 7, welcome reprieve. But it's all about periodic properties and periodic trends. As we look at the elements on the periodic table, as we move left to right, or as we move top to bottom, or from one corner to another corner, what trends do we notice? What patterns do we see? That's what this chapter is about. All right. And so just a first brief introduction about, hey, how did we develop this periodic table? We got Dmitri Mendeleev and Lothar Meyer coming up with some same conclusions about elements, putting them in order. Lots of people were trying. These two came up with about the same idea at about the same time in 1869. And so you see here at that time period, we only had these elements up to kind of these yellow ones. We had a good number of elements that we still hadn't discovered yet. In the kind of the paler yellow, or even these pink ones obviously down at the bottom hadn't been made yet in labs for these radioactive ones at the bottom. And we usually give Mendeleev first billing. A lot of people say, Lothar Meyer, who the heck is he? Because Mendeleev went a little bit further. He didn't just predict the order of the elements that he knew about, but he really promoted his ideas of, hey, I'm leaving blanks because there's new elements we haven't discovered yet. And I'm going to tell you what those new elements will be like. So the one that kind of got people to take notice is he said, okay, in 1871, I've refined my ideas. I think there's going to be an element after silicon below it on the table that will have these properties. And when germanium's discovered in 1886, they match them up and they say, hey, those numbers, specific heat right on there. The formulas are good. The density's good. Everything lines up. Mendeleev's, he's got some good ideas here. We should really go with this. So, sometimes science takes time to be accepted. You can see that's 15 years later. But this is why we say Mendeleev gets top billing, because he went further and said, not only do I have these in the right order, I can tell you about elements we haven't even discovered yet. All right. And so the reason for why was it the order, why did he famously have to switch some elements and leave some other gaps? Because they didn't know about the nucleus yet. They didn't know about protons, neutrons, electrons yet. When Rutherford discovers them, that the nucleus must exist, well, then someone else, Henry Moseley, says, hey, wait a minute. These protons that we're saying are in this nucleus, I bet that's what's making these elements go in this order. So he comes up with the idea of the atomic number, and with some studies with X-rays and looking at X-rays hitting the nucleus and causing things to happen, they were able to line up that, yes, this atomic number is equal to the number of protons. And that's why some things switch their order and some things don't, and how they all line up. All right, so when we put that all together, we get the idea of periodicity, which is a repetitive pattern, right? It's a period from the same position to the same thing as you go along a wave. That's a period. So this repeating pattern that we see. And so in this chapter, we're going to look at how sizes follow these patterns, ionization energy, electron affinity, and then some of our chemical properties. Oh, these elements all react with water. These elements always make this chloride. These sorts of things we'll look at in this chapter. And so for the first thing that we want to look at to help explain this, and on the AP test, one of the key answers they're looking for to explain trends always is what we call effective nuclear charge. Right? And that idea is, okay, we've got our protons in the nucleus. They're always pulling in electrons. We have our electrons on the outside. They're negative. Protons are positive. Okay, opposites attract. But especially with those valence electrons, those ones on the outside, since those are the ones that are doing the chemistry, right? Those are the ones being gained, lost, or shared. Well, then if we can figure out how those outer electrons are affected by this nuclear charge, we can explain why we see the things we see. All right, so electrons are attracted by the nucleus. They're repelled by other electrons. And the forces are going to depend on some factors. So the idea here, here's sodium. We've got 11 protons in the middle. We have 11 electrons total, but 2 of them are very close in the 1s. And then 8 of them are kind of closer in the 2s and the 2p. But then we have this one valence electron out here in the 3s. So how is this one electron on the outside going to be different? Because we've got 10 that are much closer to the nucleus, that are in between, and what we call screening it. So the idea here is that the effective nuclear charge, how much charge does an electron on the outside feel, is equal to the nuclear charge, which is Z, that's the number of protons, minus S, which is some screening constant. And so I told you there weren't many equations. This is about as complicated as it gets in this chapter for math. The screening constant, there's a couple ways of getting it. The book says, hey, let's simplify things. Let's just make it equal to the number of electrons in the core, right? So when we did a noble gas configuration, condensed one, we said, if for sodium is a neon core and then 3s1, well, there's 11 protons total. The neon core is 10 electrons. 11 minus 10 is 1. So they have here for this green line that the effective nuclear charge for sodium is about 1 for that outer electron. And so for this green line that the book's saying, hey, it goes from 1, 2, 3, 4, 5, 6, 7, 8. And then when you go to a new row, hey, back down to 1, 2, 3, 4, 5, 6, 7, 8. And it would just keep repeating as you go. The effective nuclear charge, at least for these first 3 rows, this is row 2 and this is row 3, it just goes between 1 and 8 and then cycles back again. It's repeating. Now there are more advanced methods. There's a method called Slater rules that there's in the textbook. There's an info box that goes a little more in depth, and it gets us closer to the real results. And then even the blue here, when they say calculate it with advanced methods, that's where you let computers do some work for you, and that gives you some other things. And so if you look at those more advanced, you find, hey, it doesn't quite get all the way up to 8. It gets to around 5.5, 5.8, something like that. And it doesn't drop all the way back down to 1. But the pattern is what we're after. And regardless of the method we use, the effective charge goes up till you get to the end of the row, then it drops back down, and then it goes back up again. That's the pattern we want to see. So what we want to say here is, okay, effective nuclear charge. It increases across a period. So left to right, it goes up, and it increases slightly down a group. So their green one would say it would repeat, but if we go to more advanced methods, it's a little bit more as we go down to the next row. It doesn't quite drop as far. Those are the 2 outcomes we need to know about effective nuclear charge, Z effective, but they get asked about on the AP tester. That's the justification that they're looking for on a lot of questions. Why does this thing happen? Because that element has a greater effective nuclear charge, a larger Z effective. All right, so let's talk about how can we identify why some things are the way they are, either based on Z effective or based on some other stuff. So we'll talk about atomic size here, atomic radius. And there's different ways of measuring atomic radius, and you cannot compare the two because they're 2 different methods. We have one radius called the non-bonding radius, or what we call the van der Waals radius, named after a dead guy. This is what is half the distance that separates 2 nuclei during collisions, when they're not bonding with each other, just when they bump into each other. And so as you can imagine, it's tough to get them to bump into each other. A lot of times we're looking at, can we get them in the liquid phase, or even better, the solid phase, when they're not really bonded, but they are touching, but it's tricky to do. The other type of atomic radius, which is much easier to get, is the bonding atomic radius, or the covalent radius, which is saying, okay, if we make these compounds, and we get crystals of them and measure them with X-ray crystallography, what is the distance between the 2 atoms? And ideally, you have 2 of the same atoms, and then you can just split the difference in half. And so you can't, directly compare these 2. They'll be in the same ballpark usually, but they are from different methods, so don't get them mixed up. But bonding atomic radius is the one we usually are interested in. All right. So if we look here, here's a figure of the bonding radius, and we can see the trend. As we go across, the radius actually gets smaller, right? So lithium's at 1.28, beryllium smaller, boron smaller, smaller. Sometimes you get little exceptions with the noble gases, but again, this is bonding atomic radius, and last I checked, we don't get bonds from anything other than xenon and maybe krypton. These 3 don't bond, so I'm actually a little confused about how they got those numbers. But from left to right, general trend, it decreases. There are exceptions. So famously, copper is an exception, where we go from 1.24, then we go up to 1.32. But then we keep going back down again. So, don't worry about those exceptions. Again, general trend. Left to right, the radius decreases. And that's because of Z effective. As we go across the row, the effective nuclear charge is increasing, so those electrons are being pulled in closer. That's what they have there, increasing Z effective. All right? As we go down a group, from top to bottom, it gets larger. And they say N increases. And we have to remember, what's N here? N is the principal quantum number, that energy level, the main energy level that these electrons on the outermost shells are in. And so with the AP test, they do want you to phrase it just so. They don't want you to say there's more electrons, because the stuff on the right has more electrons than the left. What they want you to say is, as you go down the column, the outer electrons are in higher energy shells, higher Ns, which are farther away from the nucleus. And so that's why the whole atom gets bigger. The outer electrons are farther away. So you gotta kind of remember that. As you're going left to right, it's about Z effective increasing. As you go top to bottom, it's that electrons are in orbitals with higher energy or higher energy shells, higher energy orbitals, which are farther away from the nucleus. All right. With ionic radii, here we're going to be taking the neutral atom and then removing electrons or adding in electrons. And so it starts out by looking at the neutral atom. That's what all these yellow ones are. So it does depend on the nuclear charge. That's kind of your baseline. But then it's, well, how many electrons are we adding, or how many are we removing? So as you look here, as you remove electrons, it gets smaller because the electrons don't repel each other as much. There's fewer electrons. They get pulled in closer. It's also the case, a lot of times you notice, hey, that's getting really small for some of them. Because if you think about it, like lithium here is 1s2, 2s1. If we get a +1 ion and remove the 2s1, now the configuration is just 1s2. We've removed an entire shell, an entire energy level. We don't have the 2s anymore. It's just 1s. So it can get a good bit smaller. And all of these, right, +2. Well, beryllium +2 is, again, 1s2. These all have the same configuration, so they get very much smaller. That's why you see these big drops for the cations. For the anions, you're adding electrons, again, to look like a noble gas, and so they want to spread out more. Now, we're not going to a different orbital here. We're just filling in the orbital, but because we're filling them in, we're pairing up electrons, they want to spread out. That first electron does make the anion get very much bigger, right? We get a big jump to fluoride, a big jump to chloride, a big jump to bromide, even though it's still in the same orbital. So that one's just a little bit weird there. But then you'll notice when you add a second electron for oxide, sulfide, selenide, it doesn't get that much bigger because the first one kind of spread out as much as they need it, maybe more than they need it to. So the second one only spreads out a little bit more. So that's a little bit weird, but hey, that's what happens. All right. So the general trends we want to know here, cations are smaller than the parent atoms because you've removed the electrons. The electrons don't have to spread out as much because there's fewer of them. We've reduced the repulsions. Anions are larger because now we've added in electrons that have to spread out because you've increased repulsions. So you got to spread them out so that we can decrease those repulsions again. All right. The other thing that will come up a lot on the test, or just my quizzes, because this is a great question, is when we have an isoelectronic series. Iso means something's the same. So isoelectronic, the same electron configuration, the same number of electrons. Ionic size in an isoelectronic series will always decrease, again, with increasing Z effective or increasing nuclear charge. And for these, because they're all isoelectronic, we can just look at how many total protons are there. So it says note increasing nuclear charge with a decreasing radius as the atomic number increases. So as we go here, all of them have 10 electrons. Oxygen only has 8 protons, and it's up here at 1.26 angstroms. I should have noted that earlier. For atomic radii, for ionic radii, angstroms is the unit we tend to like to use. It is 10 to the minus 10th meters, so it's not a metric prefix, but we like to use it because most atoms are on the order of 1 or 2 angstroms, so it's a really convenient number for us to use. So oxide here, 1.26 angstroms. As we increase to fluoride, gets a little smaller. Sodium gets a bit smaller. Magnesium gets smaller. Aluminum, even smaller. So all of these have 10 electrons, but as we get more and more protons, the radius gets smaller and smaller. All right. All right, well, let's talk about removing those electrons. Next trend, ionization energy. The definition is it's the minimum energy required to remove an electron from the ground state of a gaseous atom or ion, which just means, okay, you're going to pick away one of the outermost electrons, but only one at a time. All right? So we say the first ionization energy is the energy to remove that first electron. So there you're saying, here's my atom, I'm removing the electron, now I have a +1. And then a second ionization energy would be, okay, I have a +1 ion, let me remove one more electron, which would be 2 total, to make a +2 ion. And then the third ionization energy would be, okay, remove the third. And it says here, note the higher the ionization energy, the more difficult it is to remove an electron. There's a nice table in the book. I don't think they, oh, here it is on the next slide. We'll get to it. But yeah, each time you remove it, it takes more energy. Why would that be? Well, when you have a +1 ion, it's shrunk down, right? We said when you have a cation, the radius shrinks. That means the electrons are now closer to the nucleus. They're going to feel a greater effective nuclear charge. They're going to be more attracted. And so then to remove that second electron takes even more energy. And then it shrinks down some more, the +2 ion. And so it'll take more energy to remove the third. There's also, when you look at this table, you'll notice, hey, this stair step, there is a giant gap. So to remove one electron from sodium, not too bad, about 500. To remove a second, 4,500. That's a giant jump. Okay, magnesium, 700, 1,400. Okay, there's an increase, but not too bad. Then suddenly, almost 8,000. Then same thing, 500, 1,800, 27. Okay, same ballpark. Suddenly 11,000. Why is there this big jump? So I actually want you to pause the video here for a minute and think to yourself, why would there be a big jump after 1 electron for sodium, after 2 electrons for magnesium, after 3 for aluminum, and so on? What's happening there? Okay, and hopefully you figured that out. The hint here was that they labeled inner shell electrons. After you've removed that number of electrons here that are in the kind of light blue, that's where you're saying, hey, wait a minute, I've dropped down an energy level. For sodium, the first one, we're removing from the 3s orbital, but to remove from the second electron, we're removing from the 2p, because we've gotten to the neon configuration. All these are neon core and then something. So for magnesium, okay, we've removed 1 from the 3s, we've removed a second from the 3s, and then a giant jump if we try to remove 1 from the 2p. Because those are inner shell electrons, core electrons. And same thing, aluminum, 1, 2, 3 electrons, not so bad. You try to remove that fourth, you're trying to remove from 2p, nope, too much energy. So this is also why it kind of stops. Why does sodium only make +1 and not make +2? Costs too much energy. Why does magnesium only do +2 and not +3? Too much energy. All right. Also, why don't I get a +5? Well, there's for like phosphorus. Well, you see here, there's a giant jump to go to +6, but even +5, that's a ton of energy. It's increasing the same ballpark, but that energy is higher than that one. It's easier to make a sodium +2 than to make a phosphorus +5, which means, hey, wait a minute, phosphorus is nonmetal. Maybe there's something else we can do to get that noble gas configuration. So general trends for ionization energy, specifically for the first, it increases across a period, because again, Z effective is increasing. It decreases down a group, because as you go down the group, again, those electrons are in orbitals that are further away from the nucleus. They're higher energy, so it's easier to remove them. Right? And if we look at S and P block elements, we'll see a bigger range there. Once we get to D block and F block, there are much smaller variations. because now you have more shielding, going back to Z effective, because when you go to transition metals, right, you're adding into the 3D after you've removed from or added in the 4s. So those 3Ds kind of tuck inside. They're closer to the nucleus. They screen more. But we don't really have to go into that. Just most questions you'll see on ionization energy are going to be, are you in the same column or are you in the same row? And if you're in the same row, it's probably row 2 or 3. All right, so here's the whole table. So you can see here, yeah, we've got that small increase generally across the transition metals. There are, again, some exceptions, but it happens. So smaller atoms tend to be the highest ionization energy. So up here, helium, neon, fluorine, they do not want to lose electrons. The bigger atoms go right ahead, very small numbers. And again, depends on effective nuclear charge, depends on the average distance. So the ones that are farthest away and have the lowest nuclear charge, they have the smallest ionization energy. As we have higher effective nuclear charge, smaller radii, they get bigger, or higher ionization energy needed. Now you do notice there are some exceptions here. There's this exception here with nitrogen and phosphorus where it goes up and then it drops back down for oxygen and it drops back down for sulfur. You can even see it right here. It's higher for zinc and then it drops back down for gallium and indium here. What's going on there? So for these irregularities, I don't like the way they word this here, so I'm going to kind of reword it. They say it's not followed when the added valence electron in the next element enters a new level or is the first electron to pair. What I would prefer to say is it costs less energy to remove an electron if the resulting ion is more stable. So we saw here, it takes less energy to remove an electron from oxygen than it does from nitrogen. Why is that? If I remove this down arrow from oxygen, what I'm going to be left with is P3 configuration where, hey, it's up, 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 like nitrogen. And we just said in chapter 6, hey, Hund's rule, if it's up, 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 you get extra stability. You don't have to worry about the repulsion from pairing these electrons up anymore. So because removing the electron from oxygen gets you that extra stability in what you're making, it costs less energy. But for nitrogen, if you remove this electron, well, now you're messing up that extra stability. You're already stable with up, up, up. If you remove that, you get rid of it, so it costs more energy. The same thing then happens with when you add in to an extra level here. Beryllium's at 899, boron's down at 801. Well, why does it cost less energy to remove this? Well, boron is 2s2, 2p1. You're into a new orbital. If you remove this electron from the 2p, now we're just back at 2s, and we don't have to go up in energy anymore for 2p. So that's why at the end here, when we fill in the D's and go back to P, or fill in the S and go to P, we get that drop in energy. And again, when we're half filled, especially with the p orbitals, you can see it here, half filled p orbital costs more energy. And when you remove an electron from that fourth spot to make the P3 configuration, it doesn't cost as much energy because you're making something more stable. All right. Specifically here about electron configurations of ions. When we remove electrons, we always remove them from the highest N value. So the highest number in front. So for lithium, we had 1s2 and then 2s1. We lost the 2s1 electron. This is where we talked about in chapter 6 for the transition metals. When we add things in, we add in the 4s first and then we add in the 3d. But when we remove them, oh, and this is a typo here. This should be iron plus 2. Apologies for that, I didn't catch it. But we remove those two 4s electrons. So iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. If we have a plus 2 iron, we remove the 4s electrons first. And that happens for all the transition metals. Remove the s electrons first. For anions, we just fill them in to the next available spot. And they get filled to ns2, np6. They always gain enough electrons to be like the noble gas. So fluorine is 1s2, 2s2, 2p5. Fluoride, we add one extra electron to get 1s2, 2s2, 2p6. All Last trend that we'll talk about in this part of the video is electron affinity, and this one is probably brand new. We don't talk about this in Chem 1 when we do some of those others. Electron affinity is like the opposite of ionization energy. This is the energy change when you add an electron to a gaseous atom. So here it's chlorine plus an electron to make chloride. That's electron affinity. What's the delta H for that? It's actually exothermic for most elements, even metals. A lot of metals, if you add an electron to them, it's exothermic. The trick is, well, why doesn't this happen all the time? You have to remember that for delta H's, for Hess's law, we can add all the delta H's together. So while ionization energy is a positive delta H, we got to put energy in to remove them. Later on, we'll learn about, hey, when we make ionic compounds, when the plus and the minus get together, that releases a ton more energy. So overall, that's a more exothermic process. Trying to make negatively charged metals and try to make compounds out of those, it's not as good, so it just doesn't happen, even though we could add electrons to metals. And we do in some exotic cases. We just won't worry about it here. All right, the general trend is in a group, up and down, we don't see a lot of change, right? All the alkali metals here are less than 100. The carbon column, they're okay, negative 120, 130, 120, 100, not a big change. The halogens, 300, 300, 300, basically 300. So in a vertical column, not a lot of difference in electron affinity. The key is when we go across the row, we see two things. Generally, as we go across the row, it gets more negative. Right? Negative 60, negative 120, negative 140, negative 300. We got more and more negative as we went left to right. We're going to ignore noble gases here because, well, they don't tend to form ions. But we have a couple exceptions. And again, just like with ionization energy, it's when the resulting thing will mess up a stable state. So right now here for the 2A column, the s orbital is full. It's 2s2, 3s2, 4s2, 5s2. That's stable. If we add in an extra electron, it has to go to the p orbital, and that's going to cost more energy. So you see positive, positive, barely negative, barely negative. It's not very stable to do that, so it doesn't tend to happen. For the nitrogen column, again, these are half filled already. If we add in an extra electron, we're going to mess up the up stable configuration. So you see here, nitrogen doesn't want to add just one. It's endothermic to do that. It's also endothermic, or not as exothermic for phosphorus, arsenic, and antimony. You see, okay, silicon is more exothermic to gain an electron. Sulfur is more exothermic. Phosphorus, doesn't want to do it. Now, this isn't to say that it won't happen. Nitrogen, we know, does form a negative 3 ion because, again, looking at the overall delta H, it will be more exothermic for this to gain 3 electrons eventually. Same thing, the other exception, 8A, the noble gases, they're positive because they're already full up. If we add an extra electron, now we got to go to the next energy level. So that's really not going to happen. Now, I do want to make a note here that they don't in the book. This is only for the first electron affinity, adding 1 electron. As soon as you go to add 2 electrons, everything becomes positive. And so, oxygen, to make it O-1, it's exothermic. To make it O-2 from O-1, it's endothermic. But again, overall, when we form the ionic compounds, when we put plus and minus together in a nice solid crystal structure, that's what we call lattice energy. That's what we'll get to in a later chapter. That lattice energy is just incredibly exothermic. That stability you get from making it solid. So it's okay. It makes up for the energy you had to put in to make a cation. It makes up for whatever energy you had to do to get a negative 2 or a negative 3 ion, and you will get a ton of stability from that. All right. That is the end of this first part on the general trends as we go left to right or up and down. In the next part of the video, we'll talk about, well, if we look at a specific group or a specific area on the periodic table, what other trends, what other chemical similarities do we see? All right, so have a nice day, and I'll see you in that next video.